Video Explainer 8.1, Hooke's Law, number 51. Hooke's Law describes an ideal spring. Many real springs are described by their storing force, F of the spring times S equals minus K change in S minus Q change in S cubed. Where Q is constant, consider spring K equals 250 newtons per meter and Q equals 800 newtons per meters cubed. How much work must you do to compress the spring? 15 centimeters. And B, by what percent has the cubic term increased the work over what would be needed to compress an ideal spring? This is important. I think let's do these real springs and ideal springs because I'm going to go over the difference between those in a second, but this is important to note. So those are keywords here. Key ideas for this will be forces, Newton's third law, work, kinetic energy, and Hooke's law. What is Hooke's law? So Hooke's law, F equals minus Kx, x being change in S from before, and minus K is a spring constant. A spring constant will show us how much work is required to stretch or compress a spring. Tight spring is hard to stretch, so K is higher, and a loose spring is easy to stretch, so K must be lower. So K is 250 nm cubed, and then S is 0.15 centimeters, which will convert to meters because remember these are in meters, so 0.515 meters is how much we're compressing the string. So those are our knowns. We're writing that down. We're taking note of that. All right, so work equals Fs. And this is like the common equation that you'll use, right? Work of the spring, work is equal to force times displacement. But for spring, this just describes a constant force, right? So in a graph like this, right? It's what's this area, right? It's the area under here. But what we're trying to find is a real spring, because that's not how it works. Like, right, you're pushing on a spring or something's pushing on a spring. Like if you're doing that, right, you're not going to be applying the same force throughout. So it's going to be crazy. So we're going to want to find the area under this curve. And you're going up and down, so it's an integral. So we're going to find the integral of the change of work equals minus, and we're doing minus because remember this is Newton's third law. So we're compressing the string, so it's going negative. We're getting a force pushing back on us. This is negative because it's not being stretched, it's being compressed. So that's why that negative there is important. Force times displacement S. And remember our force was K, change in S, minus Q, change in S cubed. Find the integral. So K, S squared over 2 minus Q, S4 over 4. We plug in our variables from before because we have all of those, and we get 2.9 joules, joules being the unit for work and energy. And for number 2, we're going to do an ideal spring. So, right, an ideal spring, see, a spring, the force, it's moving up at a constant rate, right? So we'll want to find the area under here. That's 1/2 K change in S squared. Kind of think about that. If this is K times S, right? Side times side is a rectangle. Let's try 1/2 K times S squared. Pretty simple, right? What's what we do an ideal spring? We plug it in. Then we just do the work minus the ideal work over the work, right? To get a number, times that by 100. So we know that Q is only 3.4%. That's how much it's changing it by. That's how much the cubic term is increasing it by. I think it's important to note here, right, the negative, making sure we're setting it to negative because it's compressing, not stretching, right? So the change in distance, the force it's going in, those are important. And then also just noticing when you're finding the integrals of what and where, right? Because it is easy to see this problem to say work equals F times S, well, and just plug things in left and right and get a thing. But we're trying to find how much it's changing, and you can't just get a change with the equation we've got. We have to find the integral because that's telling us what's happening all under here because it's not constant. In an ideal spring, in a real spring, it's not constant. In ideal, we know that it would be constant. So those are important things to notice so you don't get it wrong.